Like I said, I'm a recovering physicist, and I got into sort of the data science, data analytics world, and I found that my obsessive compulsive need to keep data in order kind of came into play. It was really like an asset all of a sudden. And so all these years that I'd spent analyzing a bunch of physics data, now I could start working with business data and making sense of it and making like real insights that don't require me to spend 6 years of my life to get a thesis. And so I kind of crossed over and I maintained sort of the education aspect. So I had been teaching physics classes and math classes and computer science and astronomy and things like that. And then I jumped into teaching data science. And so that's where I became a senior data scientist at Metis. And so that begs the question, what is Metis? This will not be a sales pitch because I'm terrible at those. I'm just going to tell you a little bit about it. What we do is we educate for data science and machine learning. So we have a couple different ways that we do that. One is a 12-week intensive course. So basically you sign up, you come to our office every day from 9 to 6, and we build out a bunch of projects together, and I give lectures and things like that. And we basically take you from beginning level programming up through writing your own machine learning projects and basically how to dig into business data. We also do part-time live online courses, which do not run into the streaming issues that we're having right now. And we also do some corporate training. So basically we're just kind of an all-purpose data science educator and machine learning educator. So basically what I'm about to do for you, which is kind of walk through this overview, is basically what I do for a living and on day one of the boot camp. We kind of start out by what are we going to accomplish during this thing? What is machine learning? How do we get into it? What can it do for us? That's my day job. So if you're interested in talking about that afterwards, this will be the end of the sales pitch. Just come find me afterwards. There'll be some time for me to chat. So now let's jump into the actual interesting stuff, which is there's sort of this buzzword that keeps coming up, which is data science, data scientist. If you're in the tech scene, you've probably heard this phrase at some point. And it's sort of an open question, what is a data scientist? You'll see Venn diagrams like this everywhere. And the idea is that we're basically part statistician, part computer science major / hacker / whatever you want to call it. Basically, we write code that's not good enough for software engineers, but we do stats better than software engineers. And then there's also an aspect of business and domain expertise. So we have to sort of balance all of this. We have to be able to make statistical insights, write code that can apply those statistical insights and sort of figure things out from that. And then we have to be able to apply it to whatever business we're trying to help. So if we're trying to do finance stuff, we're trying to, say, decide if a client is worth a loan, and we need to do that very quickly. I have to be able to write the code that does that, I have to be able to decide whether they're worth a loan, and then I have to be able to know how that affects my bottom line. Now that's the total data science package. What we're going to get into today is this top section, which is machine learning. We're basically going to throw out all of the business stuff, and we're going to talk about what can we do with sort of math and statistics and a bit of computer science to actually generate insights from data. So that's where we'll focus this evening. And so there's sort of 4 overarching things that you'll see data scientists doing. We organize and aggregate data. We basically, businesses find out that, hey, we've been collecting all this data on our customers for the last 30 years. I would like to know more about my customers. And so we take that data and we organize it, we clean it up, and we get it into a place where we can actually use it and do something with it. From there, we try to analyze that data and find patterns. And so what that means is if I can figure out that this customer is like this customer, right? Let's say I'm trying to sell things to people, right? Let's say I'm Amazon, and I can figure out that this customer is like this customer, and customer A bought a vacuum 6 days ago. It may be worth my while to recommend a vacuum to customer B, and it may drive a sale. And so what I'm going to try to do is find patterns like that in the data. And now that's a more advanced example, but we can do things that are simpler but are just as valuable. We then try to build pipelines to handle incoming data. And what that means is, let's say we get customer A, and then we have a new customer that comes in. We have to draw data about that person as fast as we can if we want to maximize our opportunity. And so what that means is that I'm going to be writing code that says, okay, new customer comes in, what do I want to do with this person? How do I grab the data? How do I organize it? And that's what this building a pipeline is. And then finally, this is a little more abstract, but we kind of convert these data into insights. And so what that means is I find those patterns, and then I need to make recommend crying and swearing and anger about this stage as we're trying to organize and aggregate our data, because there's a lot of ways that it can go wrong. So what we're going to focus on tonight is that machine learning part that I pointed out in the Venn diagram, and what that means is we're going to be talking about analyzing that data to find patterns and then converting that data into insights. So pretty much everything we talk about tonight will be focused on these two sections. Now, traditionally, what happened before this whole data science thing became a buzzword is we would look at the data we have, some statistician would draw a line through it, you would consider that good, and then you would move on with your life with that. And the problem that's coming up nowadays is I go to Capital One, for instance, right, some bank. They hire me to look through their data and find patterns. It turns out they have 25 million customers, right? I can't draw a line through 25 million customers very well. Even if I can condense everything down to just looking at this person's credit score, if there's 25 million of them, I'm probably not going to do a very good job. It's just too much data. And so this is where big data becomes a problem. And this is why the data science quote-unquote revolution, and I use that term very loosely because we're still learning a lot about this topic. This is where it's kind of popping up, is because let's take this example. It's a little bit simple, but if I asked you to figure out which number is missing in this set, which number is it? 6, right? Excellent. This is a small data set. Let's mix it up a little bit. Now which number is missing? 4. Takes a little longer, right? Because things aren't in order. Our brains like patterns. Our brains like things to be in order. That's how we work. So now 4 is missing. Now which number is missing?
17.
So unless my code broke, and that's possible, when I generated this number, the number 5 does not appear anywhere in here, right? And this is just a string of numbers, right? This is just one long string of numbers. And if I asked you to figure out what's missing from this, it would take you a while, right? Now let's imagine that we have more than a string of numbers. Let's say we have a person's age and their credit score, and a bunch of other things, and I said, now let's find a pattern. Let's figure out which person is not like the other, right? So that means that there's one of these for age. There's another one of these that we're going to say runs perpendicular, right? It runs out of the board, if you can imagine that. Another plane of numbers going this way. And you have to figure out, looking at all these together, how do I choose which person is not like the other, right? And so the more data we add, the more complex this question becomes, and basically the more computer science we're going to have to do to make this work. So in the olden days of 10 years ago, right, this was kind of what we were stuck with. Like, we were starting to get into some of the big data stuff, but we didn't have terabytes and terabytes and terabytes worth of numbers. Is everybody on board with that? Excellent. So now that we've got our terabytes and terabytes of numbers, let's look at a slightly more realistic example. Okay, let's make this a little bit more concrete than I wrote some numbers on the board. So let's imagine that we have that same company where we're trying to decide if somebody needs a loan. Okay? So all of you have been conscripted into my company. Good luck with that. And we're going to look at just 3 variables for right now. We're going to say age, salary, and how much loan amount they're requesting. Okay? And so the first thing that you would want to do is you would want to look back at all the people that have done this before and say, let's try to understand what causes a person to not pay me back on time. Everybody on board with that? Yeah? Good. So if I could look at this, and I could say, great, these top 3 didn't pay me back on time. These bottom 3 did pay me back on time. Let's look through these numbers and try to make sense of that and try to decide, okay, can I figure out some kind of aspect of this data set that tells me who is not creditworthy? Okay? And that's going to be really important, because if I'm loaning money willy-nilly, we're all going to fail, because you've been conscripted into my company already. So if I look at this and I plot it, so what I'm doing here is I've got age on this axis. So basically all it tells me is how old the person is, and that's going left to right. And I've got their income on this axis. And if I'm trying to make some kind of decision about whether they're going to pay me back or not, what I can do is look at, I've got the top right, my little legend. I've got, did they default on their loan, and did they pay me back, or did they pay me back here? And so if I'm going to try to draw a line, when I right? So now I've got the same 6 examples from before, but I've got some more examples. And actually, this just kind of tells you what kind of person I am. This actually goes on and on and on. There's actually about 400 examples here because I couldn't leave it alone and I had to fill them all in. So if I plot all of that data, it looks like this. Okay? So as I filled in more and more of this data, it becomes way harder now to draw a line and understand what decides whether a person's going to pay me back or not. Now I've made this a bit of a simple example, right? There's a kind of a hard line here where I can say, if they're on this side of the line, they're not going to pay me back, right? So as a loan company, if I was a loan company, that would be what I want to do. I want to find some person that can figure out where that line is. I can draw that line, and then I can make my choices from there, okay? But what if we don't have such a simple example? What if we go into 3 dimensions, right? Because if we don't have such a simple, clear data set, because I didn't generate it, right? We can see that some of these data points are starting to overlap with each other. There's not this clear, hard line like this. Some of these red data points are now up here, some of these blue data points are down here, and we're starting to get a mix of our data that's coming together, okay? So as our data gets bigger, and we want to make a more refined selection, we're going to have to get into a place where I have to start making not just lines that are clear, I'm going to have to start making real, like, if you want to go mathematical here, well, it's not important, but I could make a plane here, right? So I could draw some kind of box that tells me whether somebody is going to be creditworthy or not creditworthy. Everybody okay up to here? Anybody lost and want me to explain it again? Because everything builds from here. So if you're lost now, we need to step back.
Well, I have a general question. So
yeah.
You're measuring like yes or no on paid back, but wouldn't the bank more likely want to know like paid back up to this point, or
right.
like some kind of range?
Yeah. So I've oversimplified a little bit for the purposes of making a point, but realistically, you would want to figure out what percentage somebody pays back and see if you can predict, like, this person's going to pay back 80% on time, 15% late, and the other 5% I'm just not going to get.
Yeah.
So if you could find some spectrum like that, which we'll get into how you could do that, then that's even better.
Okay.
Okay. So what I've shown you there is that our data can get long, right? So if we go from here, where we have a short data set, to here, our data got much longer, and that introduced some complexity. Okay? But what happens if our data gets wide? And what I mean by that is we went from 2D to 3D by going from age and income to age, income, and loan amount, right? And we know that loan amount should matter, right? Because if I loan somebody $1,000, I don't care as much if they don't pay me back as I do if I loan them $20,000, right? And so I can't just stop at age and income. If I'm going to make a real sophisticated decision, I have to add more variables that I'm trying to understand. And so that's where our data can get wide. So what if I need to include also the number of previous loans that person had, right? Because if I'm trying to make an informed decision, and I have a person that has only ever gotten 5 loans versus somebody who's gotten 55 loans, I'm probably going to err on the side of the person with 5 loans, right? I'm probably going to think that person's probably been a little more fiscally responsible. That may not be true. There's probably some give and take there, but that's one of those things that you have to incorporate if you're trying to make a real informed decision. What if I can include the number or the percentage of the previous loan that person's repaid? So let's say they have 55 loans, but they've repaid 100% of them. That's better than somebody with 2 loans that's repaid none of them. Make sense? So we can start adding more and more features. These are things we call features to make decisions with, and we're going to be making more and more refined decisions as we go. And it turns out that there's a lot of things you can add. So just in this example, these are just things I thought of sort of off the top of my head. Credit score, savings account size, current job, how long at that current job, married or single, value of overall assets, number of current loans, the amount of current loans, do they own a house, do they have a cosigner, does the spouse have income, what's their education level, what's the current debt level. All of these things would help me understand my loanee better and let me make a better decision. Make sense? Excellent. Big one, that's going to come up for the machine learning. So basically what it is generic learning is, if you think back to your high school days, is a social studies teacher or history teacher telling you this is when the war happened, and you saying this is when the war happened. I have that in my brain, right? That's what we count as learning. And that's not actually what we want for machine learning. Like you said, we need something more sophisticated than that, because for our purposes, machine learning can't be about memorization. We already know that computers are great at memorization, right? We have terabyte hard drives sitting in this machine right here where it can remember anything that I've ever done on this machine. And that's not very useful for me, because let's say I go back to this plot right here, right? If I memorized something, then my only option for making a choice would be like, okay, if I get a new person here, which one of these is going to be the one that informs my decision? Right? There's not anybody close that really informs my decision. Does that make sense? And so I'm going to have to do something that's more sophisticated than just remembering what everybody's done. So what I'm going to say is that learning is not about memorization and recollection. It's about generalizing our conclusions to new examples. And when I say learning, in this case, I mean machine learning. So everything that we're going to be doing from here is trying to figure out patterns in the data and then generalize those patterns. And there's generally two types of ways that we do that. And so this is sort of the first pure machine learning term that I'm going to give you. So there's two things that we have in machine learning. They're kind of two branches of the same thing. One is called supervised and one is called unsupervised. Okay? We're going to cover a little bit of both, but we're going to say mostly in the supervised realm for today, because it's a little easier to kind of wrap your head around, but we'll touch on what unsupervised learning is. So let's start with supervised learning. First, this is my dog. You're welcome. Second, what we mean when we're doing supervised learning is that we have labels associated with it. So if I ask you to look at this picture and tell me whether it's a dog or not a dog, I'm going to have some kind of supervision that says whether you're right or wrong. Okay? So if we want to learn, in this case what we're called supervised learning, we have to provide these extra labels so that the machine can understand whether it's doing a good job or a bad job as it tries to learn. So if I was to feed this picture into like a computer vision algorithm, and we'll touch on computer vision, what I would have to do is tell it, okay, learn about this picture, now associate that with your dog. That make sense? And then I could say, learn about this picture, and I want you to associate that with not dog. Okay? And so that's the whole idea of supervised learning, is that we feed in some kind of label along with our data, and it tries to make sense of, this is the pattern I'm finding, and this is the label I want to associate it with. And so like I said, we'll actually show some image recognition stuff at the end. So the very last thing I'm going to do is show you a bunch of cool applications of machine learning because I couldn't help myself. And we'll actually dive into it a little bit there where we can talk about how this is going to work. But first we need to focus on a more traditional data so we can build up our understanding before we get into anything complex. So when we're talking about supervised learning, we have the truth about every data point. So I know that, let's go back to our loan example. Every one of those persons, I had a yes or no that was associated with, did they pay me back? And that would be the truth about that person. So in this case, I don't know anything else about them, but I know that person paid me back, that person didn't, and that's the label I'm going to try to learn from. And then what we're going to do with it is we want to build what we call a model that learns about that history. So we take all of our historical data, and we're going to build up some sort of understanding of what tends to lead to this label, what tends to lead to this label. And then the final thing that we want, and this is sort of why machine learning is so powerful, is that we're going to want predictions going forward. So that means that when I get a new customer, I can predict yes or no for pays me back based on all of the history that I've recorded, all that data I've had. Okay? And there's two sort of common flavors for supervised learning. The first one is regression, and we're going to talk about how this works in a little bit. And the second one is the one that we've been kind of focusing on right now because it's a little bit easier to think about, is classification. Okay? So the difference between these is, for classification, I'm going to end with a very specific label. Yes, no. And I'm trying to figure out what the price will be based on that. And so what I'm going to do is I'm going to start out by trying to figure out where this line needs to be in the data. And I'll show you how we're going to do that in a little bit. And once I find that, what I can do in the future is, let's say I'm looking at homes and I'm trying to decide, am I getting gypped, essentially. So I'm getting ready to go buy a home, and I say, okay, my home is 2,000 square feet. So I come over here to 2,000 square feet, I go up, and I say, okay, this should be about a $250,000 home, right? And so that's what that either red or green line, depending on if you're colorblind, is it's going to tell you essentially where your price lies based on some understanding of where that's always laid before. That make sense? Okay. We can do other things with sort of the same idea. So let's say we have the value of the Dow divided by gold over time. So let's say I'm trying to beat the stock market, essentially. What I can do is I can look at this overall trend and try to make a decision about when I should and shouldn't buy, what I should buy, what I shouldn't buy. All of that's the same idea. And if you notice, this is where I was talking about generalizing. You can see that the actual data is really crazy here, but if I had bought down here, the overall trend is up. I would have made money, given I would have had to have been alive for like 100 years. But I could have, regardless of all this jitter, I'm now learning about the trend of the data, and I can exploit that to make sense of what's going on. Okay? And so that's what we're going to be trying to do with regression. Now, one word of caution is that if after this talk you're feeling very rambunctious and you decide to go, oh, my slide changed, and you decide to go try to predict the stock market, please don't. People smarter than me have tried and failed for years and years and years. These models are not quite to that level unless you get really, really complicated, and even then you generally have to make microtransactions. You have to be selling on like microsecond scales in order to beat the market. It's just not worth it. There are better things to do with your life. However, if you do succeed, I would like some credit. So that's regression, and we'll get into the details of how we actually do the regression after we introduce the rest of the concepts. So let's jump to classification. That's the other example that I gave, where we were doing a cat, dog, yes, no. We're trying to learn about how that works. So in this case, we feed data into the machine and we ask it, what type of thing do you think this is? What type of label or target do you think this should be? And what we're going to actually end up doing is we're going to be drawing lines in the sand, essentially lines in our little graph that say, okay, if it's here, it's a type A. If it's here, it's a type B. And that's where we're going to be making our decisions. So from here, we can start understanding, like, this is the section of our space that makes up type A or type B. That make sense? Excellent. And so once we have that, we have those lines in the sand, we can start adding new data points and then decide based on those lines what type of new thing we have. So for instance, let's go back to our example of loans. If we can figure out where that line lies in our space, then we can also make decisions about yes or no. And that space doesn't have to be 2D, right? We always think in 2D, but I can go up to 100 dimensions if I want. The machine can find lines in a 100-dimensional space that make sense. The machine isn't limited to our way of thinking about things. So that's why we're really interested in basically using this. So for instance, let's say I measured a bunch of things about flowers. If anyone has ever done any type of like analytical thing before, this is the iris data set. It's very famous because this is like the toddler toy of data science. What somebody did was they went and measured how long a flower was, how wide a flower was, and it turns out that if you do that for the 3 different species of iris, you can figure out really easily which type of flower it is based on those lengths. It's very definitive. So for instance, whatever species this is, it lives in this region of this length-width space. So what I'm trying to do, aside from talking about flowers for some reason, is figure out where these lines are and use that to make my choice about what type of flower I think I have. So for instance, I could never see the flower. I could send out an intern to go measure things, and then they send me back the measurements, and I could still decide the species without ever seeing. That's what the power of this is. Make sense? So this is another example of classification, right? I ask my machine to look through the email. I ask it to say, is this spam? Is this not spam? What do you, like, how probabilistic is it that it's spam? Let's make a decision. And that's all that it's doing, is it's trying to read your email really quickly. It doesn't actually remember anything. It just looks for words and things like that that drive spam or not spam. It draws some line in the sand of saying, if this word shows up 3 times, it's got to be spam. And then it makes that choice for you. Make sense? Excellent. We can do cooler things. I don't know if they're cooler, but I think they're cooler. Like optical character recognition. So I can ask my machine, hey, what number do you think that is? So for instance, this is the type of thing that the police use to do quick identification of plates when they're walking around parking lots to see who's parked illegally. They just have a little machine that scans the license plate and reads the license plate back. So you can do things like this, and this is another example of framing a really complex thing. Like, let's try to read this license plate into just a classification problem. All I have to know is this 4 or 1? Is this 4 or 7? If I can make that decision over and over and over, then I can decide that this is a 4, this is a Y, this is a C, chain all of those decisions together, those classifications together, and I can now read a license plate just by knowing what each one of these is by making some kind of classification of what I think it is. Okay. The other thing that we have, and this will be sort of the last section before we dive into like how we do the machine learning, is unsupervised learning. And this is a little bit nihilistic, but the idea is that there's no truth. So basically, I have no sense of, did this person pay me back, did this person not pay me back? This is a different type of problem. So maybe instead, I'm trying to figure out, is this person like this person, which person is like the other in terms of being a consumer? Can I find groups of consumers and things like that? Can I figure out some kind of pattern in the data that doesn't necessarily have a true-false label or a yes-no label associated with it? And these models don't really make for predictions. What they do is they find patterns for us. And so the kind of the key example for that is what we call clustering. So here we clearly have like 3 kind of groups of data that are hanging out here. This is kind of one ball of data, this is another ball of data, this is another one. If I didn't have the color scheme up here, you basically couldn't tell one group from the other very well. But what I could do is write some kind of clever code that says, let me look at the density of this and try to find a section that looks like a group. Let me try to find another thing that looks like a group. Let me try to find another thing that looks like a group. And I can make some kind of understanding of my data without ever having to understand yes, no, true, false. Make sense? So the example that we typically use for this is the one I've already kind of talked about a little bit, which is like consumer grouping, right? If I can find, actually there's a famous example of this with Target. If I can find pregnant women on Target's website, I can market all sorts of things that I don't want to market to a 20-year-old dude, right? 20-year-old dude is not buying diapers. Pregnant woman is buying diapers forever. So what I can do then is I can try to bring all my data in, and maybe I can move one of these things around and try to find a group of consumers that look like this person probably wants to buy diapers soon. This person does not want to buy diapers soon. And so if I can make those decisions, then I can change my marketing pattern and basically optimize so that I'm returning more money, right? And so that's kind of the key example for clustering is, can I make that decision somehow? Can I find that pattern underneath? The other example that comes to mind is natural language processing. So I think this is a pretty cool graph. I wish I could claim it, but I did not make it. What we can do is we can read documents with the machine, and there's some underlying mechanisms which I'm not going to get to today because they're pretty complicated. But you can sort of start to understand that if this word shows up, this word tends to show up. If this word shows up, this word tends to show up. And if you keep track of all those correlations, just their relationships to each other, it turns out that you can do things like figure out that this company belongs to this CEO. This company belongs to this CEO. And they're all kind of equally spaced from one another. And so I can build out an understanding of which CEO is with which company just by reading documents over and over. So this was actually from reading CNN. So they just read a bunch of CNN articles with the machine. So let's jump into, we've kind of got the terms out of the way and the ideas out of the way. Let's jump into how this works. So that was kind of a really long intro to get to this point where I'm going to kind of tell you like what we're actually doing behind the scenes with machine learning. So at the end of the day, machine learning at its core is just an optimization problem. We're just trying to find one thing that we can measure and find a nice way to measure it over and over and make sense of it. So what we're going to do is we're going to choose some value to optimize. We're going to write some kind of clever code where the machine does all the optimization for us behind the scenes. So I can say, hey machine, here's the data, optimize on this, and then tell me what you did. And then from that, we can get our model by looking at the resulting output. And so let's talk about some examples of that. And so this is the point in my talk during my boot camp, whenever I'm talking about this, where we're getting ready to start talking about regression. And there's invariably some statistician who raises his hand and goes, really, regression's machine learning? that thing that I learned in high school a little bit, in college a little bit, that's machine learning. It turns out it is. It's like the most basic version of machine learning, but it is machine learning. So the reason that it is that we're going to start out by optimizing what we call our errors. So I'm going to show you basically a GIF that shows all this in action in a minute. But what we're going to be trying to do is we're going to try to find a line that is as close as possible to all the points. We're not going to allow it to be jaggy and go to every point individually. We're going to get some individual line that's as close as possible to every point. And the way that we're going to do that is try it again and see if I can find a better way to get there. See if I can find a better line. And so I do these steps over and over. I start here and then I shift up a little bit and I say, okay, great, it's a little bit better. Let's try it again. Great, it's a little bit better. And every time this error gets smaller and the overall errors get smaller across the board.
I was going to say, are you choosing optimizing on one point or are you using the combination of all the points?
You're actually summing the error from all the points. Technically, you're summing the square of the error from all the points. So there's a thing called ordinary least squares. I'm not going to talk about it today, but that's what we optimize because we like the penalties from the squares. So, good? Okay. So if I keep moving this line, you'll see that eventually I go past the point of the best fit. So you'll see that it goes up one and then it comes back. Right? And that's basically what we're doing is I'm telling it, keep trying a bunch of different lines, find the one that you think is the best, try one past that, try one before that, and then zero in on the best possible line you can find. And I'm going to set some kind of threshold. I'm going to say try 1,000 steps, and whatever step you find to be the best, we'll stick with that. Okay, that make sense? Now the key thing here, and I think this often gets lost, is that I am not telling it in the line anything besides the data points, right? So this is why it's machine learning. Because I could tell it exactly what that line should be, but that means that I have to know what that line should be, and I don't, right? All I'm telling it is, these are my data points, figure this out for me, right? I don't want to do it, you do it. And so I'm giving it some clever way, some optimizing way to figure out where that should be for me. And it never talks to me again until it gets the line that it thinks is best, right? So that's why it's machine learning and not me telling it where the line should be, because all I'm giving it is the data. After that, it's totally on its own. It rolls a random number to start the line, and then it figures things out from there by figuring out where the smallest error should be.
But you're programming it to figure out the smallest error.
Right. But I only have to program that once, right? I can write a loop, and then every time that I get data from there on out, I can just hand it the data and say, figure this out for me, right? And this is a simple example because it's only 2D, but the errors can be computed in 27 dimensions, right? Or 3 dimensions, for instance. Like all I have to figure out is if this dot was here, right? I would have some error from going here to here and here to here, right? So that would be my 3-dimensional error, but the error, the machine doesn't care. All it's trying to do is find the smallest error. It has no preference for 2D versus 3D versus 4D. It's just going to add up all those errors together and say, can I make it smaller? Then it adds up the errors again and says, can I make it smaller? So if I can do that in 20 plus dimensions, all of a sudden this thing that I couldn't do, it can do. Make sense? Awesome.
I have a question. So right here we have like an upward trend. Like what if there's some data where there's an upward trend and also a downward trend, and it would really be better if you had 2 lines?
So that's where you have to add in things like what we call polynomials. So for instance, right now this is like a y equals mx plus b line.
Yeah.
It's as simple as you can make it. But I could do y equals mx plus mx squared plus mx cubed, and it would be able to do some kind of curvy fit to understand that data altogether. It doesn't have to be a perfectly straight line.
Okay.
So it actually, if we go into multiple dimensions as well, it's going to be actually doing a plane. It can do a plane and things like that as well. So it can get as complicated as you really want it to be when you feed stuff into the data. If you, this is a little more advanced, but you can do like logarithmic transitions and things like that. So all of that's possible.
Okay.
So what about clustering? Here all we're doing is we're trying to figure out how grouped up the points are, how together they are. And so we always, the way that we're going to do that is by always moving towards places where the groups are. We're going to figure out the density, and we're just always going to step towards that. And that's going to give us our overall space for segmentation. So this is some random data. There's one group here, one group here, one group here. These X's are kind of randomly generated, and I tell them to each try to move to a place with more data. And they kind of step around, and you can see that this one's going to try to center itself in the middle of this big set of data. So it's always moving towards high density, and that's the clever step of clustering. If I just tell it move towards high density, and then at the end, grab all the points that are closest to you and call them yours, then at the end, when I get a new point that's right here, I can say that one belongs to this one, right? So if I was doing customer segmentation, if I could figure out that my customers look like this, this, and this together, then I can find groups within them by figuring out where they're dense and where they're not dense. So for instance, I could do a guess and check and try to map this into a regression that becomes a 0 or a 1 by doing an extra little fancy bit of math, right? So I can do guess and check and try to figure out how this curve should look, and that maps things from a 0 to a 1 for me. And then I can make choices based on that. So this is just regression, like we talked about, doing our guess and check with a little mathematical trick to make it look like that.
So about the previous graph of the classification, I mean, that works really nicely because there happens to be 3 clusters in the data, and we kind of try to, what if we don't know how many there are?
So that's where another algorithm like DB-scan would come into play, because it can figure out how many clusters it needs one at a time. It'll try to find a cluster. When it finds a cluster that it thinks is good and it can't find anything else to do, it will start a new one to try to find a new set. So there are extra ways to like add on to do a little bit better job of that. We can also do things like, jump over that, like building trees. So this is another famous example, is trying to predict who died and who lived on the Titanic. From their records for when they got on the boat, like I know, does this person have a spouse, things like that. You can build out a tree that makes this choice, and it turns out that being female was way better on the Titanic. You were way better to live, like way better. And so like the first thing that we can do is try to optimize for, if I make this choice, how many do I get right versus how many do I get wrong? Okay, now after that, can I make a new choice that increases how many I get right versus how many I get wrong? So I can build out this tree to make a classification as well. That's another type of thing.
So they literally mean like, right, so when you're talking about machine learning, they start talking about like trees and randomization, that's what they mean.
Yeah, so what we're doing here is I didn't make these choices.
Right, it just thinks along how you would in a
Right.
tree.
So it goes through and it says, let me try every possible choice and see which ones give me the best answer. Now let's go to the next step and make every possible choice and see which one gives me the best answer. And you can build out a tree like this that makes the best possible choices all the way down to give you the most accurate model.
So, and this is another question, because I think I was talking about classification rather than clustering. So if you have an outlier and you classify it sort of against the grain of what the closest cluster is, how, is there just a particular method of doing that in machine learning, or is that something that you have to kind of go, this is questionable, and that has to have some kind of human determination or something like that?
You can set statistical thresholds, so what we call like standard deviation type things. You could set some kind of limit on standard deviations or some threshold of, if this answer is further away from the rest of the answers than what I think is deemed proper, and that's just some threshold I set, then it would come back and say, look, this is not right. Something's wrong here. That's actually what we call anomaly detection. That's a whole other branch of machine learning as well. But when you're doing that, you can set thresholds, or you can tell it, look, anything that you try to classify, if it gets weird, make it its own class and then tell me about it later. Okay, so now the fun part. I've shown you how the machine learning can work, right? All we're doing is we're picking something, we're optimizing it in a clever way, and then we're getting a model back out, right? And if I'm being blunt and demeaning my profession a little bit, that's pretty much all there is to it. I mean, you have to be really clever, you have to be really good with the math, you have to write really complex code, like trying to figure out those trees, for instance, is ridiculous. It's thousands of lines in order to do it properly. But at the end of the day, that's all you're doing, right? And what you're doing is you're learning from this old data what you can do with new data by optimizing those things and figuring out where the lines are, where the lines in the sand are, where the groups are. And that allows you to make really well-informed decisions on data that beforehand we didn't have the ability to do that anymore, right? We didn't have the ability to look into 27 dimensions and say, this is that person, like this is the type of person that I see here. Or this person is worth a loan and this person is not worth a loan. So at the end of the day, that's all we're doing, is we're optimizing in a really clever way, using data we know the correct answer for, or patterns that we can see to make new choices. But what that allows us to do is do some really cool things in practice. So let's start with a little bit of a silly example to build up a little bit of understanding, and then we'll kind of fly through some other examples, and then we'll open up for questions. Okay. So let's start with clustering on pictures. So what we're going to build up to is, can I send in a picture, put in some algorithm, and have it learn about the colors, and make choices about what colors belong to which group? So what I can do is, every pixel in a picture, it has three things. It's like your printer. It's got R, G, and B, right? Your printer of colors that you can find. So for instance, let's find all of the things that are vaguely pink and put those together. And then let's step one more and add a little bit different pink to show up. Or let's find all the purples and put those together. And that allows me to basically pick out groups in the picture that should belong together. Does that make sense? Everybody on board with that? Because we're going to go next level on the next slide. Okay? It also allows you to make really interesting pictures that you can watch for hours and then accidentally realize that you've not gone to bed until like 11 o'clock. Because when I figured this out, I just stared at it for a really long time. Okay? So we can use this to save lives. And that's a little bit of an overarching claim that I don't make too lightly, but we've actually seen it in practice. So let's go to satellite images. Okay? And if I look at this picture, I should credit this. This is one of my students. She did this as a project. If I look at this picture, if I can try to understand what's grass versus what's water versus what's trees versus what's road, right? I can start to basically break down how this golf course should look normally. That make sense? So if I look at this picture on the right here, this is the same picture, but I've used colors to make a choice about what this thing is. So I've said that this is all grass and greenery. These are trees. This is water. This is some more trees, these are more grass. I understand, if I break this down, how this golf course should look normally, right? I understand where the grass should be, I understand where the lake should be, I should understand where the trees should be. I can make a choice about where everything should be. What happens if we get a monsoon, and the picture changes to this, right? Everything's water, right? So let's say instead of a golf course, I'm looking at some rural town in India that's right on the coast, right? And we get some kind of big storm that comes in, and I understand beforehand that houses should be here because I've taken a picture beforehand, and now where the houses should be is water, right? That's the place I want to send aid, right? That's where I want to drop in people to go pull people out of buildings. Let's bring in some food. Let's send in the Red Cross. Let's take care of business, right? So if I can make choices on these images and go from trees and grass should be here to water is here and I don't like that, right? I can literally save lives because I can understand how this picture should look and why it doesn't look that. Make sense? And all that takes is the exact same process that made this stupid thing, right? All it takes is me understanding that this color should belong together in a group, and if this color is not there anymore, something bad has happened. Now in a sunset picture, that's not a big deal. In this picture, it is a big deal, right? And so literally, with nothing more than understanding the colors of a picture, I can literally save lives, right? And people are doing this. Like, people are hiring data scientists to do this right now. We can also do things like place police properly, right? So this is all of the murders, because I like cheery topics, in Chicago in 2016. This is something I was working on for fun, right? So I looked at all of the police reports that ended up in being a violent crime. So it's either a mugging, a murder, some sort of other thing that we're not going to talk about that just gets darker and darker from there, right? And if I was going to place police, I don't need to send them here, right? Like there were like 5 things that happened, right? I want to send them here, right? And so if I can understand that data, break it down, figure out where things are happening, and then make a prediction on where the next thing is going to happen, I can put my police into motion beforehand. Right? So if I start to look through the data and I figure out that every Saturday night there's a murder near Austin, right? Beforehand, I can look at the time and say, we're due for a murder in Austin, head that way, boys. Right? And that may stop an actual murder, right? Like, you can understand, you can break down all of these neighborhoods and things like that, and you can use machine learning to make predictions about where the next crime is going to happen and prevent it. Make sense? We can also save money. Not quite as cool as saving lives, but that's also another thing that we do. Right? So let's say that you have hired a bunch of people to read documents, basically read paper, figure out what people wrote, and type it into your machine. Right? It's just data entry. If I can teach a machine to figure out what these numbers are, then I can have a machine do that, and I don't have to pay somebody to do data entry, which is basically a boring task. I did that for a while. It's not great. So this is something I did just for fun. I loaded in a bunch of handwriting data sets. I did this in like 15 minutes, and I was able to get pretty good accuracy on picking out 8s, 4s, 9s, 0s, 2s, 1s, 8, 9, 8. It's not perfect. I would like to spend more than 30 minutes. But with just 30 minutes of time, I can start to understand that. I could also win bets. So this is actually one of my very first projects. I decided I wanted to figure out if Joey Votto, Cincinnati Red, is going to make it into the Hall of Fame. He's the best. So what I did was I looked at all of his career stats and compared that to every baseball player that's ever played and tried to figure out whether he will make the Hall of Fame based on did they make the Hall of Fame or not. I now have a bet in Vegas about whether he makes the Hall of Fame or not. So if this point does not make the Hall of Fame, I am out $25. We can do something more complicated than looking at those digits. Right? I can look at whole pictures of dogs and cats. And this is getting a little more complicated. This is not quite as simple because I'm doing what we call deep learning or a neural net. And what I'm learning is that a thing that has like ears like this and a snout like this tends to be a dog. And so if you look here, this is how catty this picture is and how doggy this picture is. Right? I'm not going to get into the details of deep learning. That's a whole other thing. But that's another thing that you can do, and it's still just an optimization problem. I'm just optimizing slightly differently for different things. And I'll be happy to talk about that. We won't get into the math of it, but I'll be happy to talk about that if you have questions. A funny thing that happened when I was working on this project, it turns out that this dog is a dog. So it even learned that in cartoon form, it's picking up these ears and this kind of snout shape, and it's starting to learn that that's a dog as well.
Deep learning is like more so for images?
You can use it on images, but you don't have to. You can work on all the things we talked about. So this is kind of my last slide. I have shown you sort of the sexy pictures of data science, right? All the things that are easy to visualize. There's a ton of other things that it's used for. So for instance, fraud detection on your credit card, deciding who gets loans, weather prediction, detecting cancer from MRI scans, diagnosing diseases, stock markets, self-driving cars, image recognition, Alexa/Siri/Google, marketing, monitoring big machines like bulldozers, reading documents, Pandora's recommendation system, chatbots, cell phone system optimization, knowing when spikes are going to occur, all sorts of things like that. So that's what I've got. I'm happy to take some questions and answer what I can for you. And then thanks for coming otherwise.